All right, welcome back everybody. So we are in 5.6, which is going to focus on differential equations, specifically growth and decay differential equations. So we're going to be dealing with exponential functions for the most part, and how to deal with differential equations describing either growth or decay of values. So we'll start with kind of the main concept for 5.6, which is going to be on the separation of variables. We've already looked at this actually in the previous notes, just in kind of individual examples. So we'll just kind of specify it here and then begin working with some growth and decay models. So for the separation of variables, we're going to be given a differential equation that is just a simple expression involving a derivative. So dy over dx is going to equal some function of x or some function of x and y. And what we want to do is solve this differential equation, find a solution to it that is general. So in order to do that, what we can do then is we can separate the variables and then integrate each term separately. So for number 1 here, we've got dy over dx is equal to 3x plus 1 over y. So what we'll do is we'll move the y over to the left-hand side of the equation and the dx over to the right-hand side of the equation by multiplying both sides by those values. So this is going to be equivalent to y dy equals 3x plus 1 dx. So now with that in mind, now we've got our variables separated so we can treat each side as an individual expression and then integrate. So we're going to integrate both sides with respect to their given variables. So on the left we'll integrate with respect to y, on the right we'll integrate with respect to x. So on the left we'll get 1/2 y squared, and on the right we'll get 3/2 x squared plus x. Now we aren't integrating indefinitely, so we need to have a constant. And note both sides would have a constant, so there's really like plus c1 plus c2. But I could just move that constant over to either side. So in general, what we'll do in these cases is just put plus c on the side with our independent variable x. So this would be our general solution for the curves that are possible. If we wanted to make this a function, we could solve for y. So we'll note we can multiply by 2. So we'll get y squared is equal to 3x squared plus 2x plus c. And, we could specify maybe this is c1 and this is c2 because the value will change when we multiply by 2. But we'll just leave it as c for now. And then we could square root. So y is equal to plus or minus the square root of 3x squared plus 2x plus c. And then based on the domain we have, we could decide whether we want the square root value to be positive or negative. And so note this would be our general solution. Which is because we have this plus c that is going to be a changing quantity. So as we change that quantity, it'll shift the way that our value looks in our function. Okay, so for number 2, we can do the same thing. So we've got dy over dx, and now we're going to separate by dividing 1 plus y and then multiplying by dx. So we'll have dy over 1 plus y is equal to x dx. And then again, we can integrate both sides. On the left, we're going to get a natural log because it's 1 over 1 plus y. And then on the right, we'll get a quadratic. So we'll get the natural log, the absolute value of 1 plus y is equal to 1/2 x squared plus c. And then we can raise both sides base e. And so what we'll get is 1 plus y. We'll make that the absolute value is equal to, and then here we'll just note that this is e to the 1/2 x squared times e to the c by properties of exponents. So a sum in the exponent is the same as a product. So this is really just a constant, which means we can simply write this as c e to the 1/2 x squared. And then we can interrogate the domain and range here to figure out if we can drop the absolute values or not. and then move from there. So assuming all of our values are positive, let's say, then we'll have 1 plus y equals c e to the 1/2 x squared, which would mean that y is equal to c e to the 1/2 x squared minus 1, let's say. And again, this is a general solution. We don't know what the value c is, and as we change c, it is going to change, in this case, the steepness of our graph, because it's going to be a vertical stretch or compression. So this is going to be kind of the general rule going forward for our differential equations, is to separate variables, solve, and then for more detailed problems, we're going to get more information that we can fill in those c values for. So the next part then is all about the specific models that we're going to look at. So if we looked at the second example, this would be an example of growth and decay, since we have an exponential model here, minus a constant, but still an exponential model overall. And so we're going to look at what general exponential models are going to look like where we're dealing with growth or decay. So we get exponential growth or decay models when the rate of change of our variable y is proportional to the value of y itself. In other words, the derivative of y with respect to whichever variable we're working with, in this case it'll typically be time, we're going to get that the derivative is equal to a multiple times a constant of that original function. So in other words, the function is a part of its own rate of change, where it's just a percentage change of that value of the function. And if y is a differentiable function of time, such that y is greater than 0, and we get that derivative, then solving this general equation is going to give us the generalized solution, y equals c e to the kt. So c is the initial value, k is going to be the proportionality constant, so that's going to be the value that we're multiplying our original function by, and exponential growth is going to occur when k is greater than 0, and then decay will occur when k is less than 0. All right, so if we have e to the negative x, that's going to be a decay function, whereas if we have e to the positive x, that'll be a growth function. All right, so let's go ahead and prove this real quick. So we'll separate our variables here. So we're going to get dy over y is equal to k dt. Note k is just a constant. So we'll integrate both sides. On the left, we'll get the natural log of the absolute value of y. And note we're going to assume here that y is greater than 0. And on the right-hand side, we're going to get k times t plus c. And then again, we can raise both sides as the exponent's base e, and we'll end up with y equaling ce to the kt, because again, e to the kt plus c is the same as e to the kt times e to the c, which is just our constant, capital C. So you don't need to reprove this. You can assume that if you've got a proportional relationship, so the derivative is equal to a number times the original function y, then you're going to end up with an exponential model for your original curve, for your general solution. All right, so let's go ahead and look at a few examples here. So for number 1, the rate of change of y is proportional to y. When t is 0, y is 3. And when t is 2, y is 6. So we know that y of 0 is 3 and y of 2 is 6. So we're going to need to use those values. And we want to know the value of y when y is 4. So y of 4 is what we're solving for. So we know that the rate of change of y is proportional to y. So that means that dy dt is equal to k times y. And when we say proportional, we mean directly proportional. So there is another type of proportionality where we would say inversely proportional. And in that case, you would get k divided by y. So in other words, the rate of change changes with the inverse, the reciprocal value of the function times a constant. Okay, so, but for growth and decay models, will be directly proportional. So then we know that y is equal to ce to the kt, and now we can use our two given values of y to solve. So we know that at 0, so t is equal to 0, we're going to get 3 is equal to ce to the 0 times k, which is just 0, which means that c is equal to 3. So that's pretty easy. And then if t is equal to 2, we'll get that 6 is equal to 3e to the 2 times k. So note here, now we're using that value of c after we've determined it. So we'll get 2 is equal to e to the 2k. We can take the natural log of both sides to get 2k. So k is going to equal the natural log of 2 divided by 2. And now we've got all the values that we need to find the next value. So if t is 4, then we'll get y is equal to 3e to the natural log of 2 over 2 times 4. So we'll just note this is actually going to work out pretty nicely. So just doing a little bit of work off to the side here. So the natural log of 2 over 2 times 4 is equal to 2 times the natural log of 2, since 4 divided by 2 is 2. And then if we use the power property, we can rewrite this as the natural log of 2 squared, which is 4. So note, we can rewrite this as e to the natural log of 4, but that's just 3 times 4, since e to the natural log will cancel out by inverse operations. So we'll get y is equal to 12. So part of this will be essentially once you get your model determined, you're just going to be solving an exponential problem where you're plugging in values that are known. All right, so let's go ahead and take a look at number 2. So radioactive decay, so half-life. So the half-life of radium is 1,620 years. If there are 10 grams of radium, how long will it take to decay to 2 grams? So for half-life, you can choose which model you want to use if it's not given. So I'll just choose the model n of t is equal to n naught times 1/2 to the t divided by k. So in other words, this will be the initial value, and then half-life is going to be the amount of time it takes for half of the substance to decay. So k is going to equal 1,620. So for this model, we've got 10 grams of radium to start, and it's going to be t divided by 1,620. So our goal is to figure out when it decays to 2 grams. So we're just going to set this equal to 2. So then we can divide by 10. Cancel out that coefficient, and we'll get 1/5 is equal to 1/2 t over 1620, and then we can take the log of both sides and use the power property. So now just bringing down that t divided by 1620 by the power property, and then we can isolate t. So we'll get the natural log of 1/5 over the natural log of 1/2 equals t over 1620, which means that t is going to be 1620 times those two numbers. And obviously our answer is going to have to be bigger than 1620. So let's go ahead and calculate that. So we've got 1,620 times the natural log, natural log of 1/5 is 0.2 or 2/10, and then the natural log of 1/2 is 0.5. And we get 3,761.5235. So maybe we can copy that. Oop. Yep. Or not. So 3761.5235. 5235. All right. So again, this should feel like a review problem really from back in 3+. And in most cases, you're not going to need to memorize a half-life formula. So those will either be given to you or you'll be given a simple exponential model for them. All right, so last one, population growth. Same idea. Suppose a population in an experiment increases exponentially. So we've got exponential growth, and we know on the second day of an experiment, the population is 100, and then on the 5th day, there are 800. Approximately how many bacteria are in the original population? So P of 0, our initial population, is unknown. We know that on the second day of the experiment, we've got 100, and on the 5th day, we've got 800. And I guess actually this is worded a little bit oddly. So we want the population on the first day, so not on the 0. So a little bit oddly worded, but nonetheless, we can figure out P of 1. All right, so let's go ahead and note that we know that our model is exponential, so y is going to equal CE to the KT. And we know the values on the 5th day and the 2nd day, so we can build our model based on that. So let's go ahead and do that. So we know 100 is equal to CE to the 2 times K, and 800 is equal to CE to the 5 times K. And so we've got this system of equations. We need to solve for one of the unknowns. So we'll just note here that we can solve both of these equations in terms of C maybe and set them equal to each other. We could take a ratio of values. So there's a couple of different choices that we have here. So what we'll note is that proportionally, we could say CE to the 5K over CE to the 2K is equal to 800 over 100. And again, that means that we can cancel out C by division, subtract our exponents here, so we'll have e to the 3k is equal to 8. And that's going to mean that if we take the natural log of both sides, 3k is equal to the natural log of 8, which means that k is equal to 1/3 natural log of 8, but 1/3 we can bring up as an exponent, so 8 to the 1/3 is just 2. So k is just the natural log of 2. So then if we want to know our population on the first day, on the original population date, note that y of 1, we need to find c. Oops. So we can take either equation and then isolate for c. So note, let's use the first equation. So we'll have ce to the 2 natural log of 2, which is equal to CE to the natural log of 4, which is just equal to 4C. So 100 equals 4C, which means C is equal to 25. So then our population, I guess, P of 0 would just be 25, or P of 1 would be 25 e to the natural log of 2. So whatever that value would give us, which will be a slightly larger value than 25. Again, the wording is kind of off on this, so I'll update this on the notes so that it's more clear what we're looking for. I think we want our answer to be p of 0. All right, so that's going to conclude the first portion of the notes. So if you have questions, feel free to shoot me an email or come by my office hours. Otherwise, until I talk to you next time, take care.